Okay, this is a warm-up. We've already done this. You just did this on the quiz. Let's see if you did it right. Okay, it says graph this function and then restrict the domain so it's one-to-one, so you know what's going to come up. It's going to be an inverse question, as you can tell down here. This is in vertex form, so let's think about the vertex first. The vertex is +3, +2, I believe. Yep. So 3, 2 is kind of up here. A is just -1, so it's the regular shape, or sorry, regular size. It's just kind of upside down. So 1 and then 4 is kind of here, and then and then 9, 5, 6, 7, 8, 9. So there and there. But again, we want to restrict this so it's only one-to-one. Oh, it says graph the whole thing. I'll graph the whole thing. Oh, but thinking ahead, let me change. I always miss that. This is different than the iPad. This part I'm never going to use again. I'll graph it. Sure, you want me to graph it, but I'm going to change color because later I'll refer to the part I want, which is just the red part. Okay, so restricted, so it's one-to-one. Again, yeah, I'm just going to use the red part. The domain, so those are the values of x where this is red. That's 3 and upwards. What's the range of the whole thing? Well, the range, whether or not I restrict the domain, it's the same range. It goes from -infinity on up to, I guess, 2, including 2. Graph the inverse. Okay, the inverse is going to be take this thing. When they ask it in this order, what they're expecting you to do is graph this before you kind of think about algebraically what the function is going to be like. So we'll just take these meatballs and we'll reflect them over the line. Over that line. That's the y equals x line. We'll reflect them over there. So this thing is going to go about here. This one's going to go kind of there. This is going to go, I guess, here. And then 5, 6, 7, 8, 9. I'm still doing the same counting. I'm just counting sideways. All right, and this one was the one that represents the vertex, so this thing is going to look kind of like that. This is a lot harder than the iPad. Okay, to hit those perfectly, but you can kind of still see my meatballs. Okay, so I reflected that across that line. Hopefully I did that correctly. That's the graph of the inverse. What's the domain of that thing? Now we can just kind of tell by looking. Sorry if that bothers you OCD kids. The domain of the blue thing is from -infinity, guess what? Up to and including 2. Seem familiar? Yeah, it's going to come from here. And the range of that is probably going to look like this. It's from 3 and upward. Okay, and then algebraically find the thing. So we start with this, but of course we reverse everything. So this is now x equals -y minus 3 squared plus 2. And get things kind of where we want them so we can find y eventually. This negative kind of bugs me. Let's just do this now. And then we take a square root. I know you were thinking this here, like, wait a minute, I thought we had to square root positive stuff. Well, x is a variable, so the opposite of x minus 2 might certainly be positive. And then this is always plus here, because I did restrict that domain. Anyway, that can turn out fine. There's this weird domain where we're going from -infinity up to 2. So basically x is less than 2 here in this inverse. So that shouldn't, yeah, it looks a little funky, but it's not impossible. That works. Okay, so here's the new kinds of problems. This is about word problems that we're going to basically need the calculator and do some really crazy graphing to try to solve. Okay, so first it's saying we've got a yard basically back here. We're going to fence in, we're going to use 200 linear feet of fencing. So basically that's saying the perimeter is going to be 200 around this thing to make some sort of rectangular area. And we're going to talk about what different kind of rectangular shapes would enclose different amounts of area. You've probably heard about these kind of problems before. Let x equal the width. I believe this would represent the width to most people because it's the shorter of the two dimensions. And what would this have to be in order for this whole thing? We're going to build this perimeter of 200 into this kind of what we're going to choose for x and the length. So if that's the width, of course, those are the same. The distance from here all the way around to this part has to represent half the perimeter. So that little length that I just built right there has to be 100. So this length along here has to be 100 minus x for the 4 of these things to add up perfectly to 200. Okay, and then it says write an equation for the area. Well, equation for the area, we just had that lovely unit on area, so you know how to do area of a rectangle. And there we go. Sketch a graph of the function. Now, you could leave it like this. Some people, this is like, well, wait a minute, this isn't vertex form. This isn't standard form. This is the same as 100x minus x squared which actually isn't really in standard form. We should say negative x squared plus 100x. That might make it easier to graph for you. It might make it easier to think about. It might make it easier to sleep at night. I don't know. Let's sketch this in an appropriate window. Let's see what this looks like. All right, so I need a new function. Or sorry, I need a new window. Press menu. Okay, I will do that. And I get graphs, and I want, and we could just enter it. You can actually enter this however you want. It's a little easier to enter it as x times 100 minus x. That's fine. Okay, horrible graph, as always. So I'm going to go menu as I always do, zoom fit, see what happens. Still not great. Drag it around over this way maybe. Actually, you can't do that as easily. I'll go menu, zoom, quadrant 1. Okay, still horrible. Now what if I go menu, zoom, fit, see what it looks like? Pretty bad. All right, so let's go menu, zoom, out. And I want to be able to see what's going to happen. Like, where does this thing start to get interesting? Okay, there it starts to get interesting. Escape. And let's zoom box this now. Menu, zoom, box. You can go through this over and over again if you really want. But I'm going to box in. This looks like it'll be an interesting window. Shows my intercepts, shows the peak, shows when it comes back down. Yeah, so now we have a nice parabola that fills the window. Okay, so let's do this. I'm going to completely cheat. The funny thing is I have to do this. Oh, I can't do this during a video. Okay, I'll be right back. Ta-da! Okay, I figured it out. I figured out how to just copy, paste, and cheat and get this right here on the page. So that's kind of an appropriate window, and you would kind of say, you know, that you went to like past 100 here and past, oh, I can't even see that now. Whatever this height is. I could look back at the calculator and tell you. That height was something like, oh, that's weird. It's a big number. It's like 3,000 or something to get that big. Okay. Now let's. What are we doing? Whoops, I didn't mean to turn the page twice. Find the maximum area of the enclosure. Okay, so we basically want to now find what's the peak of this little window up here. I'm not going to write all these steps down because you can rewind the video if you want, but I'm looking for the maximum of this thing. Oh, this was a little over here, a little better. And that's found in menu, window zoom, analyze graph, maximum. And then, of course, I have to tell it where to start looking and where to stop looking. Now, this is kind of strange. It gives me this number 50 and then 2.5 e plus 3. That means that's 2.5 times 10 to the third. Let's try changing, as we did in class, let's try changing the settings on the decimal stuff here. Float 3, again, fixed 3 was kind of helpful before. Let's try this. And if I do fixed 3, that changes it to this. So I at least see that number. It doesn't look so silly. So it's 50 and 2,500. I'll write that in. Okay, so I just found out that max point was 50, 2,500, but that doesn't really answer the question, or kind of over-answers the question. The question was, find the maximum area. Well, 50, remember, was the value of x, and x here was based on the width. And then f of x is really what my answer is kind of for this function a, so it's like the y value here. So the area here is actually just the, whoops, am I highlighting? Area is just the 2,500. Let me rewrite that better. There, so it's just 2,500, and I'm indicating here that this point, 50 kind of 2,500, was found by using the maximum function on the calculator. What are the dimensions of the garden that has the maximum area? Well, that's really what this is about. That's what that 50 is about anyway. The width is 50. What would the length be? If the x were 50, what would the other dimension be? Well, it was going to be the 100 minus that. So 50 and 100 minus 50 is still 50. So maybe you would have known that already. That's the one where it's actually a square. What's a practical domain for this model? Well, we kind of have a hint there that this thing only has positive area for these values of x. I believe this hits the axis over here at 100. So for domain, again, we're talking about what the x's could possibly be. Does it make sense to have a width of 0 on your fenced-in area? Probably not. Anything bigger than 0 probably looks kind of stupid, but it's better than 0. I don't know. We could argue all day about whether that should be a closed bracket or open bracket. But it really can't go outside 0 or 100 to even be able to build a rectangle. So, yeah, even at 0 and at 100, you could argue that's not even a rectangle. It's like the stupidest fenced-in area ever. Like you can't even walk your worm in that yard, but let alone your dog back and forth. You could probably plant spaghetti. Okay, that was a funny joke. All right, what's the practical range for this model? All right, so putting those numbers in between 0 and 100, what do we kind of get for the vertical window here? Well, we know it never goes above 2,500, and again, 0 for area doesn't really make sense. We could argue over whether or not those brackets are supposed to be round or not, but really, it's not a rectangle with any kind of area if it's 0. And, oh wait, 2,500 should be included. I really should do this though. I really should say that no, it can actually be 2500. That's the square. That's the 50/50. That's kind of the optimal. So yeah, we should definitely include the 2500. But we can't go any bigger than that. That was the maximum. He could use the fence to get more area if he used the back of the house. This is a common kind of way to do this. This is an example of one of the ways they manipulate this problem. Use the back of the house as one wall of the garden, or one side. So like there's this back side of the house here. Sorry, that was kind of strange. So this is basically up against the house, and so this doesn't count. We're just going to use the 200 for these three. So really it's only three sides of the rectangle involved in the 200 limitation. X is going to be the width again, so this plus this other side have to add to 200. So this has to be the rest of 200 minus the other two sides that have already been spoken for. So that's 200 minus 2x. What's the area of this now? Well, this is going to be, the area now is going to be 200 minus 2x times x. And you could make a graph of that. Now what I would do over here is I wouldn't spend too much time erasing all that stuff. I'd just make a great big new one. And so this is supposed to be 200 minus 2x times x. Good enough. In terms of window, I don't know. I think I'm getting better if I go quadrant 1 first and then fit. Actually, no. Maybe I think those in either order is kind of the same. Then I do a bunch of zoom outs, and then I do a box eventually. And notice how far over here I am when I do the zoom outs. I'm kind of trying to get close to the peak each time I do that. And then zoom box, and let's go from, let's see some of that, and let's see the peak. So that's pretty much what I want, and that's great. Okay, I'm going to cheat, and now I have a graph for that. Okay, now let's answer some questions. What's the maximum area of this enclosure? Okay, so I want to go back here, and I go menu, analyze, maximum, and I want to search between here and here, and lucky for me, I kept all that, I kept all that, this is hard to drag around. I kept all those defaults there, so this is 50, 5,000, so it's not totally unrelated to what I had before. All right, so this is 55,000, I'm gonna write this down here. 50, 5,000 represents that point. What's the maximum area? That's 5,000. What are the dimensions there? Well, 50 is the x, but that's 50 times, not 50x. 50 by, that's how they write that usually. This is 50, this would be 100 minus 2x, and if x is 50, 100 minus 2x is actually 100. This is a little bit different, and of course the area is bigger, so yep. Because we were able to get bigger area because that house help there. How could we determine these values algebraically? Okay, well one way to do that is to use the symmetry of this parabola. We know there's a 0, 0 here, right? Because if you stick 0 into the function, like it doesn't take it doesn't take too long to figure out the zeros of this function. Actually, this is kind of already it's almost in root form. You could find the roots really fast just by factoring this some more, and you'd find out that the roots are at 0, and I guess let's just do it. This is x, and then I could take out a 2 from that, put it out front, and then what I'm left is 100 minus x. So that's like saying negative here, and then x minus 100 in here. So the roots are at 0 and 100, which doesn't surprise me. I kind of thought that was at 0 and 100. So guess where the peak is? Guess where the vertex is if the roots are at 0 and 100? Remember that peak plus q over 2? That tells me that has to be 2. So I'll just say it this way. Roots at 0 and 100, and we call that p and q in root form. It's a q. So vertex was at x equals, or the axis of symmetry, p plus q over 2, which in this case is 50. And then I can tell where that was. And then to figure out what the 5,000 is, well, I know it's 50 times 1,000 because those are the dimensions. Sorry, 50 times 100. Where did I get that? Ooh, I'm making mistakes today, but I am catching them. I feel so smart. I could say, well, 50 times 100 has to be that area, or I could put 50 into this equation, which is exactly the same thing as doing that. And then I could basically find f of 50, and I would know that that value for area would be 5,000. As for the other dimension, I had to do the same thing I would have to do here, which is to just plug that into there too, to the 200 minus 2x. Okay, looks like I have to stop there. I'll see you in video part 2.